So, my name is Tapio Pursimo. I'm a staff astronomer here, been some years now. And we continue with the quasars and that way. Okay, so this talk will be, first I talk about quasars, it's the repetition of we have seen already. Then I will talk about what kind of data or what is the sample we are studying and sort of why, and then I will show some examples of the stuff we have observed at NOT. And the team is fairly compact. Michel Dennefeld, he's basically the driving force of this program, and then there are some other people as well. Okay, so at least we have a consensus. 3 out of 3, we have the same model of the AGN, which is certainly a good news. And first we were talking about, first talk was about the jet and the blazars which are over there, and then the previous talk was about outflows, and then just to remind you that this talk will be about the emission lines, which is basically the broadline region, which is very close to the accretion disk. So in the AGN, it is assumed that there's a supermassive black hole accretion disk, and nearby is a broadline region. And if you, in optical spectra, if you see broad emission lines, broad meaning like wider than a couple of thousand kilometers per second, then you say that it's a Seyfert 1 or quasar or blazar, whatever you want to call it. And then if you see only narrow emission lines, then it would be a Seyfert 2 or radio galaxy. That's sort of the hand-waving, not hand-waving, but that's the consensus. And it is thought that, okay, all these are the same guys, but the orientation is the main difference. And if we look at the sideways, the AGN, the dusty torus is blocking the light from the broad lines. And if we look at the face on it, then we would see the broad lines, and that would be just a simple orientation thingy. And the variability of the quasars is typically, it's not very much, but they are variable. They are not, no way, any kind of standard candles. So that was good, and then there were a couple of oddballs which sometimes they showed the narrow emission lines, but then some other occasions there were broad emission lines. And it was only quite recently when there was a systematic study using the SDSS data, and they were searching for, looking at the light curve and then just comparing the spectra from different epochs, and they found a small number of quasars which have narrow emission line in one epoch, and then they show blue continuum and the broad emission line in some other epoch. And it was noticed that it was associated with the guys which have been in like an enhanced emission, like 1 magnitude or so in optical light curve. And even though it's not, so it was turned out that it's not uncommon to have these kind of changing look quasars, but they are fairly difficult to find because you need to have a well-sampled light curve, and then you need to have at least 2 spectra, and 1 spectra with the low state and the other one on the high state. And by chance, these guys were looking at the tens of thousands or hundreds of thousands spectrum, and they found a few tens of changing look quasars or AGN. And what is been like the basic idea is that either the torus is not holy, but it has holes. So so or it has lumps, and these dust clouds are moving in front of the line of sight, and then that would block the the broad lines in one epoch, and then when the dust cloud is moving away, then depends on whether dust cloud is in front or not, then we would see the broad lines or not. The bottom panel shows, well, at least front row can see it, that it's a spectrum, and then they have added some dust in the spectrum, and then they get the sort of okay fit. So it's feasible, but the timescales are the problem. And the other option would be that there's a change in the accretion rate, so that the difference in the accretion disk, which are causing the changes on the optical spectrum. And just a side comment, the bottom panel, it's Wilford. She was a student, not student, like 15 years ago or so. So it's at least we have some results. So my work, or our work, we have looking at the light curve from Gaia, and the alert index, that's a nice source of data, because they provide the light curve, and then when it's outburst or whatever change, they give a light curve and say that, okay, this is a outbursting thingy, and then they cross-correlate whether it's a star or supernova or planet or whatever, or AGN or AGN candidate or radio source. And in our work, we are picking up obviously the AGN or AGN candidates and radio sources, and taking a spectra if we are lucky. And from the practical point of view, we are biased towards the targets which have been observed by SDSS, because there's a nice reference spectrum. And for the data, it's a low resolution spectroscopy followed by the quick photometry. And we are not observing flux standards, we are stealing the flux standards for somebody else, and I think that works fine. And the photometry is calibrated against the field stars, so we are not taking the standard stars either. And these are a couple of examples. Of course, I should say that these are typical examples, but they are not. They are sort of semi-random, nice-looking thingies. And that shows the bottom is time and x-axis, and then is the magnitude from Gaia, and the vertical lines, they show the spectrum we have taken at naught. And what you can see, that the time scales can be can be fairly short, like say months or years, and more often its time scales are more like years. And they are picking also whether the target is going fainter or brighter, and like those who have sharp eyes can see that it's up to 2 magnitudes of the outburst. And I will show spectra of this guy and this one here, and then this is a bit more carefully showed. And this one here, I talk about. And data reduction, it's boring, but it has to be done. And we have done using IRAF and MIDAS, but that's not very user-friendly. If you have one spectrum per once a week or so, or even less, you spend quite a lot of time reducing the data using IRAF. If it would be a single observing run, then it would be, I don't know, perfect, but it would be brilliant. So, So instead, I have started to use this PyBit, or whatever is the pronunciation. It's not the abbreviation, but just the name of the thingy. And it's a publicly available Python-based script, and it's very user-friendly because it doesn't have any clicking or or pull down menus or anything. It's simple command line thingy with the setup file. And one can calibrate the data against the standard start as well. If you know the filter and you know the magnitude, you just add it in the setup file, and then the flux is scaled using that one. And then you can use the same package for telluric correction. That's fairly slow, and I haven't tested that very much. I have actually started to use this only this spring, so I don't have any very thorough experience on this. And output, it's a fit stable, which is nowadays it's quite user-friendly format as well. And even I could manage to install it in my desktop, so it can't be too difficult for installing. And so I think it looks very nice, and it's fast as well. I think it's a couple of minutes per spectrum, plus of course you have to copy the files over and so and so. And then the next slide is the data analysis. That's one of the worst abbreviations what I've seen, but it's bad something. Again, that's a Python-based program, and that's for fitting the emission lines and the continuum and the host galaxy, and get the host galaxy properties as well. They are all fitted at the same time, and then using this Markov chain Monte Carlo thingy, that's quite slow, so it easily takes like 40 minutes per one region to be fit. So you don't want to do it too many times per target. So that's also like a work in progress. I need to look at that bit more carefully, and more testing is needed. Then, as I said, there are radios, so now comes a couple of examples. So this is a radio source from that catalog, which has a nice compact name, and it's like looking at Sympado and NED, it doesn't have any, it's an empty field, and from Gaia HST guide star catalog it's marked as 20 point something, and so it's too faint to be observed with reasonable time with the mid-size, bit bigger telescope, so there are no redshift for this guy from the literature. But thanks to Gaia, and should I say thanks to me, now we know the redshift, and that's magnesium 2 line, and then that's the H beta line, and redshift is a bit less than 0.8. And it's very cost effective. That this spectra took like 15-20 minutes during twilight, bright twilight, and it would need dark time using not to get the similar quality spectrum, and it would take maybe an hour, a couple of hours. And this was the guy which was basically flat light curve and then jumping up and then declining. So the black line there, that's the SDSS spectrum, which is clearly labeled over there. And then the first epoch notch spectrum is the blue one, and then that's the date, if anybody can read it. And that's the first epoch, and that's the second epoch. And that's the inset of the H beta region, and that's you can clearly see that the H beta has become much brighter or much stronger during the outburst, and also the H gamma, it's basically invisible from the SDSS data, but I would say that that's a clear detection. And this one, that was on the top left-hand corner, light curve going up in timescales of of about a year or so, and then declining now. And again, that's the SDSS spectrum. You can, well, and even with my bit older eyes, I can see that there's some change on the H beta region. And this is this bad whatever fitting thingy. That's the SDSS spectrum. That's the first epoch not spectrum, and that's the second epoch. And that's the data, is the white line, and for the line there, if my hand is not shaking too much, that's the host galaxy, I think. And then you can see the oxygen lines there and H beta, and then there is a hint of bump, like that there would be a broad H beta line. And referring to the previous talk, I think there's an outflow visible there as well on the SDSS spectrum. Then cut 2 bit later, that's the fit, and then basically the data is not good enough to see the it's too noisy and not high enough resolution, but it's good enough to see the broad line and fit it, and one can easily see that let's see, yeah, that's the H beta, so broad line is redshifted. I can't remember the number, so don't bother asking me. And then the time evolution, this was the just before the peak, and this is somewhat after the peak, and you can clearly see that the broad emission line is still changing during these epochs. And no, wrong button. So some thingies are, we can see the H beta just on the SDSS spectrum. This is the normal AGN, and we get the blue continuum, and then broad H beta is redshifted, at least from from our data. And that was it. I think I have over time. Thank you.